Welcome back to our video module on dynamics. Today, I've written down a problem for us to take a look at. We're going to imagine that we have some ball with some mass m and it's traveling with some initial velocity at a little ramp. And when it hits this ramp, it shoots up at 45 degrees and we have nice projectile motion. What I've done here is I've listed what the position and velocity vectors are as a function of time. These should look all pretty familiar to you. And my question to us today is this right? And how do we know? Today, we're going to identify new ways of checking our equations of motion. I know that for this system, we're going to have conservation. We're going to have conservation of a couple things. The first thing we're going to do is we're going to have conservation of energy, and we're going to have conservation of momentum. But let's use what we know about conservation of energy and conservation of momentum. Well, what would that look like? Let's see, in energy, we know that the change in kinetic energy equals the work. The kinetic energy at state 2 minus the kinetic energy at state 1 is going to equal the integral of f dx from 1 to 2. The kinetic energy at time 2 is going to be 1/2 m, the magnitude of the velocity at time 2 squared, minus 1/2 m, the magnitude of the velocity at state 1 squared. However, we like having things in terms of time, so that's going to be the integral of from time 1 to time 2 of f dot v dt. So now we see that by using our vectors, we have an equation that we could actually work with. Let's take a look at what this looks like. The magnitude of v2 is simply going to be the magnitude of this vector at some later time. That's going to be the x term squared plus the y term squared. Well, the force applied is just the force of gravity, so we know that's mg, and that's in the j direction, and it's negative. We're going to dot that with the velocity, which we've already used over here, the velocity at some point 2, and we see that these two are equal for all time. So by looking at our conservation of energy and pretending like energy is conserved, plugging in for our position and our velocity, we can check to see if for these positions and for these velocities, if energy really is conserved. Now, of course, this is a rather long computation for analytic solutions, but one can imagine that by a couple smart lines of code, we could check all of our computer solutions for position and velocity based on conservation of energy. We'll scroll up, and in red, what else do we know about energy? We know that the kinetic plus the potential initially should equal the final kinetic plus the final potential. Well, that kinetic energy, what is it? That's going to be 1/2 mass times the magnitude of v squared plus the potential energy, which is the force of whatever energy field you're in, times the position. We can say that's initial. And we do the same thing here. This is, on the right-hand side, we do the same thing. 1/2 mass times the final velocity, magnitude of the final velocity squared, plus the force through which something has moved times the distance through which it has moved. So we can use this red equation for all times to check our position and velocity to make sure that it's true and energy is conserved. Let's take a look at momentum. We know that the sum of the forces equals the change in momentum. So another way to rewrite that would be the integral from the initial time to the final time of f dt is equal to the final momentum minus the initial momentum. So one more step for this one is going to be from the initial time to the final time, and we know what that force vector is. That's simply mgj dot dt equals the final momentum will be mass times the final velocity as a vector minus mass times the initial velocity as a vector. So here we have a third equation that shows conservation of momentum for all time. Finally, let's do conservation of momentum in red, and we'll do conservation of angular momentum. The sum of the moments about any point, we'll say point P, should equal the change in angular momentum about point P. Once again, we say this is the derivative of the angular momentum with respect to time. And we know the moment is r cross f, so it's the integral from the initial time to the final time of the distance from point P crossed with the applied force dt should equal the difference between the final angular momentum and the initial angular momentum. The left-hand side is easy enough to figure out. We simply take the position vector crossed with the force for each applied force, and in this case we only have gravity. So let's take a quick look at the right-hand side. What would the angular momentum be? It's going to be the final position with respect to P crossed with the mass times the final velocity with respect to P minus the initial. The left-hand side should just come right down, and in this particular case the force that's applied is simply mg, just the force of gravity. So this is our fourth equation using conservation of angular momentum that should always be true for any position and velocity solution. In summary, we've learned 4 conservation equations that we can apply to position and velocity. Now in this case we did a very simple projectile motion, but one can imagine that with numerical analysis we can apply these for any solution we come up with that will tell us if in fact we are right. I hope this video gave you a basic understanding of how we can use conservation equations to check our work. Thank you, and I look forward to seeing you in our next module.